Hello guys, I'm Nikhil and this is the introductory section for the fast Fourier transform. The polynomial multiplication using the fast Fourier transform. So before going to the fast Fourier transform, we need to know few things. Let's consider a polynomial. Suppose say it is 1 plus x. So the degree of polynomial is the highest power of the x here. So here it is x raised to 1. So the degree of this polynomial is equal to 1. Consider an equation, different equation where 1 plus x square plus x cube is there. Then here the degree of polynomial will be 3. Now let's see another representation of polynomial. Consider an equation when y is equal to 1 plus x. Now if we evaluate the value of y, putting the value of x as 0, then y will get the value of y as 1 plus 0 equal to 1. Similarly, when we put value of x as 1, we will get value of y as 1 plus 1 equal to 2. We will get value, if we put value of x as 3, we will get y is equal to 1 plus 2 is equal to 3. So we have got these pairs like 0, 1, 1, 2, 2, 3 and so on. If we calculate, for calculation of each of these pairs, it will take a round time of theta of n. But to represent a polynomial completely in the point value representation, we need to calculate n such values. So if we are calculating n such values, the total time that will be required will be theta of n square. That's why we need theta of n square time if we convert a polynomial from coefficient representation, which is nothing but this, into the point value representation. Now you can plot these points onto a graph with the x and y axis, where this is the x axis, this is the y axis. You can put this value as x value is 0, y value is 1. So this is the first point. Then x value is 1 and y value is 2. So this is the second point, which is 1, 2. This first point is 0, 1, and so on. So this will create some wave. So we can consider this as a signal. So we have represented a polynomial. We converted a polynomial into the point value representation, and we have plotted these points, which are nothing but the point value representation of polynomial, onto the graph. And so it is. So we can say that a polynomial is a signal. So if a polynomial is a signal, then we can apply various techniques in the digital signal processing for manipulating the polynomials. So let's say we need to do a polynomial multiplication. Suppose say 1 plus x into 2 plus x square. So these two polynomials can be represented as two different signals, and using the digital signal processing, we can efficiently multiply these two, process those two signals in order to get a signal which is the signal representation of multiplication of these two polynomials. So this is the basis where we convert the problem in the algorithmic space, which is nothing but of polynomial multiplication into the fast Fourier transform of two signals. Hi guys, I'm Nikhil, and today we are going to see the polynomial multiplication using fast Fourier transform. So how fast Fourier transform is important is there are multiple representations in which a polynomial can be represented. So first one is the coefficient representation of a polynomial. So if you convert coefficient representation of a polynomial into point value representation, this conversion takes time of around theta of n square. Now if when you convert two polynomials which are in the coefficient form into their respective point value representation, then the multiplication would simply take theta of n time to get a point value representation of the product of the two polynomials. But since you want to multiply two polynomials, you have to convert the point value representation back into the coefficient form. Which will take time of around theta of n square. And if you directly multiply two polynomials in the coefficient form, for example, like 1 plus x square and 2 plus x, if you multiply these two polynomials directly, it will also take time of around theta of n square. Now it is important to reduce this time, because if you consider a scenario where you have a CD player and and you are playing the music on the CD player, so the CD player generates around 44,100 signals per second, and if you want to apply an equalizer to it, so it is like as good as multiplication of these two polynomials which represent your music, and one represents your equalizer sound wave. So if you want to multiply these two polynomials in shorter time, then there must exist some algorithm so you can reduce it from theta of n square. So this is the point where the fast Fourier transform comes into picture. So what fast Fourier transform does is it converts the coefficient representation into the point value representation in time of theta of n log n. And using the inverse FFT, you can convert the point value representation into the coefficient form, inverse FFT, with the time of theta of n log n. So if you want to multiply two polynomials, you can do this in the time span of theta of n log n plus theta n plus theta of n log n, which is nothing but equivalent to theta of n log n. So your time reduces from theta of n square to theta of n log n, which is a really huge difference in signal processing. So let's see how it does it, how the FFT does this. So FFT is nothing but an extension of discrete Fourier transform with the application of divide and conquer strategy. Let's see an example. Suppose you have given an equation minus 2x cubed plus 1. You need to represent this equation in the vector form, and this equation is as good as 0 1 into x raised to 0 plus 0 into x raised to 1 plus 0 into x raised to 2 minus 2x cubed. So you can have the vector representation of this as 1, 0, 0 and minus 2, where 1 has come from this, 0 has come from this, and the 2 has come from this value, minus 2. So now we apply the divide and conquer strategy to this. So we do not take the consecutive numbers, but we take values with distance of 1. Like you take a pair of 1 and 0, and this is the first pair. So you divide it like this, 1 and 0, and you divide it into the other part where you take 0 and minus 2. This is also a vector representation. You divide it further using the divide and conquer strategy into further smaller part, which is 0 minus 2, 1 0 and 0 minus 2. Now what we do is we compute the fast Fourier transform for each of these, and it turns out that if you have a single value, that is, this value will represent like 1 plus 1 into x raised to 0, that is equal to 1, and similarly all these values. So these values return themselves. So how this value return themselves, that we will see in a minute. So these values are calculated as below. Now let's say n is the value of the input, which is equal to 1 for, let's say, this one. Now there's another factor, which is omega of n. Omega of n is nothing but the complex root of unity, and for each omega of n, there are omega of n is equal to e raised to 2 pi I k upon n. Now for this omega of n different values exist depending on the value of k. So k, if it is like k equal to 0, k equal to 1, k equal to 2, this happens till k is equal to n. So for each omega n, there are different, there are n number of values depending on the value of k. So let's say omega n represents that. It is equal to e raised to 2 pi I k upon n. And we compute the final value as omega, let's say. Here is the value of k. Here is the value of a0, let's say. And here is the value of y0. So the vector we have, that is here, is a single input vector, that is there is only one value, which is 1. And we will calculate the y0 value. And k starts from 0, so let's take k equal to 0. So e raised to 2 pi I into 0 divided by n, which comes out to be e raised to 0, which comes out to be 1. So value of omega is going to be 1. Now let's compute this equation. So if we substitute this value of x into this equation, it comes out to be 1 multiplied by x raised to 0. Now we substitute this value of omega in the value of x. So 1 into 1 raised to 0, which is nothing but 1 itself. That's why this vector 1 will return the value of 1. In similar way, this 0 will return the value of 0, this 0 will return value 0, this minus 2 will return vector minus 2. Now, what happens is, now here in the combination phase, we have got value 1, 0 for this vector. So let's compute that. So here n will be equal to 2. This is omega n, this is omega, this is k, this is a0 and a1, which is our vector 1, 0 in this case. We have taken this one from here, we have taken this 0 from here. These two values were written by in the combination phase below this node. And we have again the value of y0 and y1. So what we do is, here we put the value of k, we take the initial value of k as 0. So omega n is equal to e raised to 2 pi I k upon n. So here n is 2, so e raised to pi I k. Now k is equal to 0, so e raised to 0 and is 1. Now let's take another value of k as 1. So it will be equal to e raised to 2 pi I k upon 2. This is 2. So e raised to pi I k. Now we substitute this value of k equal to 1. So e raised to pi I. Now e raised to pi I is nothing but minus 1. How it comes is, the equation for any e raised to x I is equal to cos x plus I sin x. In that way, if you compute it using this trigonometry, you will get this value. And these values are nothing but the complex roots of unity, which are represented like this. This is the plane where we have this value as 1, we have this value as plus I, we have this value as minus I, and this value as 1. And the complex roots of unity are taken in pair. Like if you take only one complex root of unity, then you will get value this. If you need two roots or complex roots of unity with the value of k0 and k1, then you will get roots in this pair. If you take 4 roots, the roots will go this way with the value of k ranging from 0 to 3. You will get root like 1 plus I minus 1. This is minus 1. Sorry, my mistake. And the value minus I. So we will see that later in the chapter. So let's compute these values first. So here we were here where we got the value of omega as minus 1 for value of k as 1. Now what we do is, for the value of k equal to 0, we calculate the value of y0 as by putting this term in the equation. We put as 1 multiplied by x raised to 0 plus 0 multiplied by x raised to 1. So this will come out to be, and we will substitute the value of x as the value of omega which we have got. So 1 multiplied by 1 raised to 0 plus 0 multiplied by 1 raised to 1. So this will turn out to be that 1 multiplied by 1 plus 0 is equal to 1. So you evaluated this value of y0 against k equal to 0. Now you will evaluate the value of y1 against k equal to 1. So let's compute this value here. So you will evaluate like this: 1 multiplied by x raised to 0 plus 0 multiplied by x raised to 1. Now we will evaluate the value of omega omega which is equal to -1 in the value of x. So 1 multiplied by -1 raised to 0 plus 0 multiplied by -1 raised to 1, which also turns out to be 1. So this vector in the combination phase will return another vector which will have value 1 and 1. In similar fashion, we can calculate the value for this vector where 0 and -2. So let's compute that. If we put n is equal to 2 and omega n, omega k a0 a1 and y0 y1, and we have the value of vector 0 and -2. So we put the value of k equal to 0 initially, which is e raised to 2 pi I k divided by n. Omega will turn out to be 1 since it is equal to e raised to 0. Now for k value of k equal to 1, it will turn out to be e raised to 2 pi I k divided by 2 is equal to e raised to pi I is equal to -1, which we calculated previously. Now we will substitute the values: 0 multiplied by x raised to 0 minus 2 multiplied by x raised to 1. Now we will put the value of omega in x. So 0 minus 2 into the value of x is 1, which we took from here, and it will be equal to -2. In similar fashion, we calculate the value of y1 for value of k equal to 1. So let's calculate that. So 0 multiplied by x raised to 0 minus 2 into x raised to 1. Now we will put the omega minus 1 in the x. So 0 minus 2 into -1 raised to 1. So it will turn out to be 2. So this vector in combination phase will return the value -2 and 2. Now we have got two vectors, 1 1 and -2 2 in this phase. Now we have to calculate the last phase where we will get the 4 values, which will be nothing but the FFT for this vector. So let's do that. So here n will be equal to 4. This is the omega of n, this is omega, this is k, and this is a0 a1, this is y0 y1 y2 y3. We have 4 values of y, since we will get 4 points in the output. So we will basically get a polynomial of degree 4. That's why we are taking 4 values of y, y0 to y3. And we represent now. There's one point we need to consider is we have to take this vector in a different fashion, where you represent this vector in this form 1 1 and this vector as -2 2. Now in evaluating y0, y1, y2, y3, you will evaluate them on the basis of these pairs 1 -2 and 1 2. And in that also, you will evaluate this first pair only for y1 and y2, and you will evaluate this second pair only for value of y1 and y3. So let's do that. So this is equal to e raised to 2 pi I k upon n, which is equal to e pi I k upon 2, because we evaluated 4 in it. So value of omega, which is for k equal to 0, we will get is 1. For value of k as 1, we will get the complex root of unity as -1. Sorry, it will be plus I. For k equal to 2, we will get this value as -1, and for k equal to 3, we will get this value as -I. You can check this by putting the value of k in this equation, where you will get using the formula cos of x plus I sin of x, and you will get this value. But these values are nothing but the complex roots of unity, which we have got. Since we need 4 complex roots of unity, we take these complex roots of unity by going clockwise, anti-clockwise. So let's compute y1 first, which will be 1. This is the first pair we will take. 1 multiplied by x raised to 0 minus 2 multiplied by x raised to 1. We will put the value of omega 1 here. So we will come. This will turn out to be 1 minus 2 into 1. It will be 1 minus 2 equal to minus 1. Similarly, we will calculate y2 with the same pair. Now we will take the value as this one, minus 1. So 1 multiplied by x raised to 0 minus 2x raised to 1. So 1 minus 2 into minus 1. So it will turn out to be 1 plus 2, 1 plus 2, it will be 3. Now we will calculate y1 with this pair, the second pair, as 1 into x raised to 0 plus 2 into x raised to 1. We will evaluate the, we'll put this plus I in the x, so 1 plus 2i. Similar fashion, we will calculate y3 with this second pair and putting the value of x as minus I. So we will put it like this. We are using the second pair, 1 plus 2x, 1 plus 2 into minus I. So 1 minus 2i. So the pair we have got here is minus 1, 1 plus 2i, 3, and 1 minus 2i. You will return. So this is the vector which we have got through all this calculation, and is nothing but the answer of FFT of this. So this is the final answer which will be written by these two, and which is minus 1, 1 plus 2i, 3, and 1 minus 2i. So this is how the FFT works. So the basic funda of this is, in FFT we do nothing but we evaluate the polynomial values against the values which are given by the complex roots of unity, which is nothing but this. So by evaluating, by doing the evaluation of the polynomial against the complex roots of unity, we get the fast Fourier transform in shorter time span. And the shorter time span is basically achieved through the technique of divide and conquer, which takes a logarithmic time of n log n. So this is how we improvise the signal processing, which we explained earlier in this. And one point to mention is, the conversion of coefficient representation into point value representation is called as the evaluation, which we just did against the complex roots of unity. And conversion of point value representation into the coefficient representation using the inverse FFT is called as the interpolation. These are the digital signal processing terms. And another digital signal processing term is when we multiply two polynomials, or when we calculate, or when we multiply two signals, it is called as the convolution. So let that be multiplication of two polynomials in the point value representation or the coefficient representation. Both means the same term, which is the convolution. So this is how the FFT works. Thank you.